Hi, good evening and welcome to this course of Fundamentals of Electrical Engineering. The instructor is Professor Debapriya Das from IIT Kharagpur. And there are 3 TAs who will be taking this doubt clearing classes. I will take this Monday 6 to 8 p.m. session. My name is Shatrugn Shide. I am a PhD scholar at IIT Bombay Electrical Department. And my work is on machine design. My PhD topic is about designing and sizing of electrical machine for given rating and application. In this course, at the very end, you will get to learn about 3 electric machines, one rotating, one static, and 2 rotating electric machines. So fundamentally, the flow of course is like this, that we will have to watch the recorded videos on NPTEL and solve the assignments. These doubt clearing classes are to help you in solving those assignments. So the regular flow of my class, what I generally do is at the very beginning of the class, I start with doubt clearing. That is, if you have any doubt from the lectures of this week or maybe previous week, today is the first week only, and then we go for problem solving. Mostly we go through the problems of last year's assignments, and if you have some other problems from your mind or somewhere else, you can ask. So again, welcome you all to this course. I think you have attended 1 or 2 sessions last Saturday, and I would hope that before coming to the doubt clearing classes, you would complete the lectures, all the lectures of the week. Before I go any forward, could someone please confirm that you can hear me?
Yes, sir.
Okay.
Yeah, we can.
All right. So most of you are first year electrical engineering students, or is there an exception?
Yes, sir.
Okay. All right. So the first class is mostly about very basic circuits and power. So we'll start with doubt clearing. So any doubt you have from the class, from the lecture, so something else you can start with. You can ask questions.
Hello, sir.
Yeah, Shushant.
Good evening, sir.
Good evening.
Sir, I have a question that is it necessary for an alternating current to be varying periodically?
Okay, no, it is not necessary. Anything that, say for example, even it is not necessary to vary sinusoidally. Say for example, if you have a current or voltage, whatever, which
Okay.
varies like this, let us say, then also it is alternative. In fact, it may not be periodical also. If it changes direction, it is alternative. But this is not pure AC. Pure AC means the average over a period must be 0. Then only you can call it pure AC. But the supply that you get at your home, that is periodic, the voltage
Sir,
and current.
if the graph of current is in only a positive x-axis and it's like a hilly graph, is it okay?
Like this?
No, sir. Like the first graph you have done random graph, like it's only in the positive x in the first quadrant only.
Like this?
Not uh, yes, sir. Like that. Is it AC?
No, this is not AC. This is DC.
Sir, but it is not constant. Like it's coming up and
No,
down.
DC does not need to be a constant. It can be varying. This is DC. The waveform that I drew here, number 2, if I write, this one is also DC. This is called a sawtooth waveform. It looks like the teeth of a saw. This is also DC. DC does
So
not
what
necessarily has to be a constant.
type of DC current is it?
What type? There is no type,
Uh,
just DC.
okay, sir.
It's varying DC. Have you guys studied Fourier series in mathematics yet? Or Fourier thing is, any periodic waveform, if you see, say if I write, say for example, take this sawtooth waveform that I drew here, or maybe if you look at a square wave or anything like this, any periodic waveform, say I write is say a function f, which is a function of say theta, f theta, that can be written as a DC component plus a summation of AC components, okay, of different frequencies, say frequencies of say f1, 2f1, 3f1. In this fashion we can write. So in that way, if you see this red waveform that I have drawn here, this one, this you can divide into a DC component, you can split up into a DC component and several AC components like this. So it contains AC components inside it, that is for sure. But overall, if you look at this waveform, you cannot call this an AC because it is not changing its direction. This is DC. In fact, even if it touches zero and again becomes positive, then also it is a DC.
So, a square wave is DC.
Depends. Say the square wave that I have drawn here, say this waveform 3, this is not DC, this is AC. But if the
Okay.
square wave looks like this, if it is like this, then it is DC. This is DC. This is AC.
So,
Yeah.
so my second question is, can you explain the difference between battery voltage versus voltage and EMF of a battery?
Voltage and EMF of a battery. EMF is the force and voltage is potential difference. Okay, so say you have a network, say maybe a very complicated network, and there are several nodes in the network. You put the voltmeter between any 2 points, what you get is the voltage. Okay, now if you have a cell, then generally what we get here, not generally, what we get here is the EMF, the electromotive force. What happens is, this is the internal resistance of a battery, and you will never be able to access this point. What you have at your disposal is this, and this is the EMF of the battery, this E.
So you are not audible, sir.
You cannot hear me because I have
So
not
is
muted
it
myself.
clear, sir?
Can you hear me now?
Yes, sir. Can you explain the
Okay.
again, sir?
Yeah, what I said is, so this is a battery. Okay, now please mute yourself, Pavan. Now, what you have at your disposal is only these two terminals. This green box is the battery, and you cannot touch inside the battery. So this part, this is not accessible to you. Only this terminal and this terminal is, these two are accessible to you. Now what you get, the potential difference between these two is we call the battery voltage. Now when there is no load on the battery is simply kept open, and assuming that the voltmeter has perfectly infinite impedance, then the voltage that you will get at the terminal is the EMF of the battery. Otherwise, if there is load, then the voltage will drop. The voltage that we get across the load is the battery terminal voltage that keeps changing with the load, but EMF is constant, assuming that there is no chemical change in the battery while it is supplying the load.
Sir, is it a potential difference and voltage same? Like,
Yes,
Okay, sir. And sir, battery voltage, sir, difference between battery voltage and voltage.
No difference. It's a potential difference.
Okay, thank you, sir.
Nothing. Same thing. If there is not a battery, then you can call it a voltage. You can call it, say, a voltage across a resistor. You cannot call it a battery voltage across a resistor, right? So only when there is a battery involved, when you are measuring its voltage, then only you can call it battery voltage.
Sir, there was a definition in the video that voltage is the energy per unit charge created by the separation. What it means, sir?
It's about, suppose there is a positive charge present here, right? Now it creates a field like this, and the field, what is a field? A field is, as far as I can remember, it is 1 by 4 pi epsilon naught. Tell me if I am wrong. This is q1 by r squared. Field is the force per unit charge.
Yeah, right, sir.
So if field is the force per unit charge, then what you get is, you have another negative. It can be positive also, doesn't matter. Let us say positive. These are equipotential lines. So you have, say, another positive charge here, q1. It has some potential. Now if you want to move q1 by this distance, say r or r1, say, now q1 is here, so you have to do some work, right? So this work, how much work you have to do, that is depending on the charge q1. That depends on, okay, I said q1, so q2. So the force that you have is q2 times E, and the work done work done is this times the distance, so F times S. So in this case, if I write, say, mod F times R1. Now you said work done per unit charge, right?
Yes, sir. Yes, sir.
So divided by the charge, you will get the voltage. Basically, it's the unit work done or work done per unit charge to move a unit charge in the electric field. How much work you have to do if you have to move it against the field.
Can it is be defined as like, sir, energy gained by a unit of charge as it moves through the battery?
Dimensionally, I have to check. Energy gained by an unit charge. Yes, I think.
Okay.
Yeah, other questions? Questions from others? Any more questions? Okay. Do you know the difference between voltage source and current source? Or what is a current source? Do you know?
Like, say, it a voltage source, it may be AC voltage or DC voltage.
And current source?
It's producing current,
A voltage
a
source
fixed.
also gives you current. Go ahead.
Yes.
A voltage source also gives you current then.
Yes, sir. When we connect the circuit,
Then what is
like
the difference between them?
source transformation, like.
No, not transformation. Say, can we not have a current source in reality?
Yes, sir.
Source transformation, what you are talking about, that is about a trick of solving the circuit. That is one thing.
Yes,
But
sir.
what is the difference? What is the voltage source and what is the current source?
Don't know, sir.
Anyone else want to try? How many of you have watched all the videos? Can you please raise a hand? I just want to take a stat.
Yes, sir. Sir, I can define it.
No, wait. I'm not for this. I'm just taking it. Okay, lower your hands. Anyway, okay, go ahead. Who said you can define?
Sir, voltage source and a source type of source, this frequency is different types.
Frequency? No, DC voltage source, let us say. DC voltage source, DC current source. A DC voltage source would give you a constant voltage irrespective of the load, and the DC current source would give you a constant uh, current irrespective of the load. And it's not about DC. For AC also you will get the same thing. Now you may say, how can I say it's a constant AC voltage? So when we say constant AC voltage, what we mean is that the two attributes of the AC voltage, the amplitude and the frequency, they are constant. They are not changing. Okay. All right. Let us discuss one more interesting thing. Maybe if we get some more time, I will discuss even more about this voltage and current sources. All right. Suppose I have an AC source, AC voltage source. Okay. Like this. And I say that the voltage V equals, say, V sine omega t. Now I have several questions. First question is, when I say, when I write this small letter, lowercase letter V or I, whatever, what does it mean? What does this lowercase indicate? See, I have written V equals V sine omega t. This V is lowercase, this V is uppercase. So what is the meaning of a lowercase variable or lowercase
RMS
letter?
RMS
No,
value.
no. Lowercase means instantaneous. Always keep this in mind. This is an international standard and no one can ever assume that I am writing lowercase as RMS or something. This is invariable. Never ever mix this up. Lowercase means instantaneous. When I say capital V here, this is amplitude. You can write constants like amplitude, RMS, or DC value as capital. But when you mean instantaneous, something that is a function of time, you have to write it as lowercase. Okay. Now you will get to see that in books or maybe in lectures, when they show, say, AC voltage, they also give a potential like this, plus minus. Maybe when they show AC current, say I write, say, I equals, let us say, V sine omega t minus phi. There also I give a direction, an arrow. My question is, AC voltage or current keeps changing its direction, then what is the point of giving a plus minus n? Because if I write plus minus, after 20 milliseconds, the plus minus direction changes, right? For same thing is for current also, the direction changes. Then what is the point of giving this plus minus in AC voltage? Or is it at all correct to give a plus minus n in AC voltage and current? Any idea? Sometimes AC, not only AC, potential difference is also shown as arrow like this. So what is the meaning of this? Having plus minus in AC circuits. Does it make any sense? Any guess? This is wrong, this is right.
Sir, this is a current voltage,
This is a
like a alternating voltage source.
that is true, but can I write plus minus? It keeps changing, no, the direction keeps changing.
So it represents terminals of that source.
Terminals are represented like this. Terminals, okay, like this.
Sir, when we draw a sine curve also, there also we
Hmm.
put the positive and the negative signs, which is representing an alternating current.
Sine curve, do we show positive and negative sign? We draw like this, say voltage I write in terms of time.
But there is no point in doing the positive and the negative sign. There is no what mentioning it in an alternating current.
Okay, we will look into the answer. Thing is, suppose you are measuring potential difference between 2 points. Now, when you are measuring potential difference anywhere, it is always measured with respect to some point. Say, for example, if I say the voltage across this is B, and I write this, say, VAB. This means potential of A with respect to potential of B, which basically can also be said as, say, there is some other point, say O, potential of A with respect to O minus potential of B with respect to O. Okay. Now look at this waveform. Say when I say V equals V sine omega t. Right? Say up to 0 to 10 milliseconds. Let us say it is a 50 hertz supply. So 0 to 10 millisecond, the point of potential A, so the potential of point A was more than that of point B. How do I know that? I know that because during this time V was greater than 0 and I have put plus at the A terminal and I have put minus at the B terminal. So this means that whenever I write V for this voltage source as V sine omega t, I am measuring potential of A with respect to B. So if I find that at some point of time V is positive, that means A is at higher potential than B. And if I write V is negative, that means B is at higher potential than A. Okay. So in this source itself, if you want to write minus here and plus here, you have to write V equals minus V sine omega t. Right? So in AC sources also, the same is the thing for current also. Same is the thing for current, which direction the current is flowing. Say at any point, if I get I greater than 0, that means the current is showing along the arrow direction that I have drawn. If at any point we find that I is negative, that means current is flowing in opposite direction of the arrow that we have drawn. So in AC circuits also, whenever you are writing expressions for voltage and current, if you do not show the potentials like this, that has no meaning. Okay, just like DC circuits, it has no meaning. I do not know with respect to which point the potential is being measured. Is it clear now? Why is this required? So without writing or without giving this direction of EMF or voltage, whatever, if I write V equals something V sine omega t, that makes no sense. You guys can see my screen, right?
Yes, we can see.
Okay.
So can you summarize what you have said, the region?
Say, for example, forget AC. For example, you have some element in a circuit, DC circuit, and I say that the voltage across this element is 10 volt. Would you not ask another question? Or is it sufficient to say that the voltage across this element is 10 volt?
No,
Then what else we have to mention?
we need the potential. I mean, where we have a positive potential, where we have negative.
That means with respect to which point have you
Yes.
measured the voltage? Is it voltage A with
A to
respect to
B,
B or B with respect to A?
A respect to B, and we can measure B respect to A also. Just polarity
Right.
will differ. That's it.
So if I draw it like this, we can say that B is at higher polarity, higher
Yes.
potential than A.
Yeah.
Similarly, if I write that the voltage here is 10 sine 100 pi t, then also it matters whether I write plus or minus, because
Yes.
to you it may look like it is changing very fast, 50 times a second. But instantaneously, if you look for every second, say for, if I say for at t equals 5 millisecond, t equals 5 millisecond, what is the voltage? Can you tell me?
Sine.
It will be at its peak,
100.
10 volt.
Yeah. Okay. Maybe. Yeah. Sine 100 by is 1. Okay. Yeah. 10.
So at its peak, 10 volt. Now the question is, where is this 10 volt? Who is at higher potential? If I write like this,
B.
then only we can say B is at higher
Yeah.
potential. Now if I say at t equals 15 millisecond, it will be minus 10 volt. That means at this moment, at t equals 15 millisecond, A is at higher potential than B of 10 volt.
Mm.
So
See,
until,
I mean, yeah. I mean, let it this. I mean, we practically. I mean, speaking right. I mean, we can say I agree. I mean, we can say now B is higher potential than A. So can you give me some glimpse on why we are saying in terms of charge point of view? For example, I agree. I mean, positive side, negative side. Can you tell me in that way, like charges? So in that would be
charges, why means charge means it depends on the current. We are not talking
correct.
about charge, we're talking about voltage.
Voltage correct. I mean, see, now we are saying uh, B is having more potential than A, right? What do you mean by more here? I mean,
That means if I have, say, a resistive element, then the current will flow from B to A.
yeah.
That is the definition of more potential, higher potential.
I mean, just conventional current flow you're telling.
Yes. There is an unconventional current also. I do not know about.
Okay.
No, you said conventional current. What does it mean?
I mean, opposite to electron direction.
Okay. So is it understood? So in AC circuits also, if you do not light this plus minus sign for voltage sources or arrow for current sources, that doesn't make any sense. That is it clear?
Sir, can we say the plus and minus sign only represents which is at higher potential or lower potential? Just
Not
to
higher, lower, not higher, lower. Say like this, that when I say for any element, the voltage is V, that means that voltage V instantaneous or DC, whatever, that voltage V is measured at the positive terminal, positive mark terminal with respect to the negative mark terminal.
Okay, sir.
This plus minus, you will see at some places they also draw arrow in voltage sources also. That also means the same. You are measuring the voltage of the arrowhead with respect to the arrow tail.
So it's normally means the meaning of polarity of voltage, no? Like some point is that much higher than that point.
It is the same thing, no? What I said here, t equals 5 millisecond is 10 volts, so it's 10 volt higher, 10 volt above than point A, point B is 10 volt above point A.
I have
So
one
in
more
the
doubt. Yeah, go
Yeah,
ahead.
one by
Go
one.
ahead.
sir, in the first lecture, sir asked a question about if we have rating of bulb like 40 watt, 60 watt, then what will be the diameter of that filament, tungsten filament?
Okay. So the thing is, when you say you have a bulb of 40 watt, again, that is not a complete definition, because you have a bulb of 40 watt. Say in India it is 40 watt, you take it to Japan, it will be much lesser, much less than 40 watt. Because in India the voltage is 230 volt, Japan it is 110 volt. So when you say 40 watt, you have to also mention what is the voltage rating of the bulb. Say it is 230 volt. So if you connect that bulb to a 230 volt AC source or DC source, if it is a filament bulb, then the power that the bulb will consume is 40 watt. Right? Now from here you can find out what is the resistance of the filament. Can someone quickly do and tell me what is the value of R? V square by P. So something you will get. Now resistance is given by rho L by A. L is the length of filament, A is the cross-section area of filament, and rho is the resistivity of the material with which the filament is made. Now, if you have these two information, resistivity of the material and the length of the filament, you will get to find what is the required cross-section area of the filament.
Okay, sir. So like basic difference between circuit or network is what? Like you are using sometimes circuit and network.
I don't know. I think there is no difference. Maybe complex circuits is sometimes called network. Or is there a difference? I will tell you next, but I do not think there is one.
In the lecture, sir said that like it may be open or closed, but a circuit need to be only always closed, but a network can be open like that.
Okay, that way. Yeah. But a circuit can also have open terminals. Say, for example, say I have a circuit like this. Now this is the open terminal. Now what will you call this circuit network? Circuit also, because current are flowing here, current is flowing here, current is flowing, but no current is flowing here. Call this a network maybe, but that doesn't mean that as soon as you short circuit this, it becomes a circuit. It's not like that. It's not that hard and fast.
Okay, sir.
Suppose these three resistances are R1, R2, R3, R4, and this is V. and I have short circuited these two terminals. Can you tell me in this condition what will be the current through R4? In terms of V or 1 or 2 or 3 or 4?
Yeah.
Sir, is there short circuiting that point?
You tell me. I am asking.
Sir, if short circuited,
No.
then through R4 the current will be 0. I think.
Is it
No,
short
no
circuit?
short.
What do you think?
No short circuit. I mean, it's just if we think we have to. No short circuit actually. Those resistors are parallel only. I think R3, R4, and one more. Right.
On this terminal, if you go like this, can you see any impedance in the path? Nothing. It is short circuited. Current through R4 will be 0. Okay. Now we'll look at the, okay, any more questions? Mahesh was going to ask something.
Yeah, actually, I have one question. See, for example, when we have a problem like current is going, some current is going to the conductor. Okay, I mean the time is like sometimes we used to see 0 to some particular time. Sometimes we used to see negative to some positive particular time. Here negative, we I mean they mean that the
I'm sorry, what are you saying? Some current is flowing.
okay, for example, the in a conductor some current is going conductor or you can take it anything. I mean this
Okay,
current is
whatever.
flowing actually. Okay,
Hmm.
flowing the time interval. Some problems may have 0 to some particular time, 10 millisecond you can take it. Okay,
Okay.
and some problems may have minus 10 millisecond to plus 10 millisecond. You
Okay.
can take it that way. Here the time period before 10 is it's a kind of kind of the current or charge already we have. That is what we trying to mean negative time period, or for example in a capacitor, right?
No, it's not
Some
like that. Are you talking about
okay,
negative time?
yeah, negative time. For example, in capacitor, we can it can hold some charge before the supply given to the.
Yes, the thing is like this, that
So
sometimes we
what?
say, see if you have a cap or maybe something else also, I will give you one more. If you have a switch here and say a resistance, we say that the capacitor was holding some
Initially
charge
charged, I
such
think.
that it had 10 volt across it. So, and say at t equals 0, I close the switch. What we say is at t equals 0 minus
Yeah.
capacitor voltage was 10 volt. So
Yeah.
this is used to show initial condition. I do not think in this course a negative time concept will appear, but I will give you one small example, like Fourier series that I mentioned. Some what we do is for in periodic waveforms, say I have a periodic waveform like this, sometime not in some other cases also, sometime in order to analyze it or in order to make the analysis easier, what we do is we assume that, not assume, in the analysis we take that t equals when t is negative, it was like this periodical. Similarly, it was after t equals 0, and we analyze it for one period, say like this from here. It's not one period, sorry. It is one period, going up. So maybe from here to here. Sometimes we analyze like this. This is only for analysis purpose.
Okay.
So there is no such significance. I'm not very sure where you got this.
Practically, what we trying to mean negative side. I mean, positive side is okay from 0
Negative
to 10
time we take
millisecond.
mostly to make the analysis easy. Or sometimes what we do is in complex circuits, say when we have several modes of operation, say mode 1, mode 2, mode 3, like that. Say you are analyzing mode 3, then some time of mode 2 is a negative value. In that way it comes.
Sir, is it like initial charge of capacitor?
Yes, initial charge of capacitor or initial current of inductor.
Ah, yes.
Yeah, then that's my question actually, and then it applies only through the charge storing elements, not like resistor. If resistor, they are just they
Yes,
can't
you
give
can
like
say.
negative to
You can say.
so yeah,
It's like
that's what my
Say you are,
question. Yeah,
transient analysis.
maybe yes.
yeah, that's what I mean. It's kind of memory the element had before. Memory in the sense, I mean, kind of
Do
charge
not
or
talk about
flux.
memory. Let us say energy. Energy
Yeah, I
stored
mean,
in the
yeah, you
element.
can take it that way. Energy, it had.
Memory is a very difficult term.
Yeah.
Okay, since we talked about capacitor and resistors and inductors also, let us look at these basic elements quickly. Okay, so first let us say resistance. Okay, whenever we study this polarity is very important. These resistance are whose polarity, whose voltage is this V with the shown polarity, and a current is flowing in this direction.
Hello, hello. Hello.
Just a minute. Can you hear me now? I think I lost my internet connection. Hello.
Yeah, yeah, we
Yeah.
can.
Can you see what I drew here? Resistance I drew. I said
Yeah.
that voltage polarity is important. Voltage polarity and current direction. So if you have a resistance with the voltage polarity as shown in the figure and current direction as shown, what is the relation between VI and R?
We could simply that's it.
V equals IR.
Yeah.
All right. Resistance. Now we have inductor. Similarly, I will write, let us write VR, okay, voltage across resistance. Subscript R, I am not multiplying. Okay, let us not write this, this may be confusing. Again, an inductor, pure inductor, V, L. Current is flowing in this direction. What is the relation between VI and L?
Equal to
V equals to L di by dt.
V equals L di dt. Always remember, when you are writing V equals L di dt, this must be the directions of voltage and current. If you think, okay, we will look into it. Let us complete this discussion and we will look into that. So resistance and inductor are done. Resistor and inductor. Third one is capacitor like this. Again, voltage direction like this, V, capacitor C, current flowing like this. Relation between VI and C.
I equal to C dV by dt. Or
What? Say again.
I equal to C dV by dt.
I equals C dV dt.
By,
Okay. See one thing. In this whole discussion, I have written V and I as small letters, lowercase letters. Very important. Never mess this up. When I write this in lowercase letter, this means it doesn't matter whether this quantities are DC, AC, sawtooth, or whatever. It is instantaneous value. Instantaneous, what is the voltage across the inductor? that much will be the slope of current through it. That's it. You need not be bothered about what is DC or AC or something. This is a very general equation, no exception, applicable everywhere if there is an inductor, pure inductor. Understood? Don't mess these things up. Always make sure that whenever you mean instantaneous, you write lowercase letters. Okay, now what I was saying is, sometimes people get confused about the direction of voltage and current in inductor, because we study in physics like this, that Faraday first said that E equals d psi dt. Then experimentally, Lenz said it's the negative, right? That means voltage will resist the change of flux. Now the question is, I have written V equals L dt. I did not write minus L dt. Why so?
It's back EMF only, right? L.
Let us look into it. So say I have an inductor L and some current here is flowing. Right? Now say this current I is an increasing current. So if the current is increasing, what is happening? The flux in the inductor, that is increasing. True. So if the flux is increasing, then the inductor will try to stop the increment of flux, Lenz's law. Right? So it will try to create a current in this direction. How would it try to create a current or try to stop this current? By applying a voltage in this direction. Right? In this direction means this is at higher potential, this is at lower potential. That means if I write a voltage like this V, then this V is positive. Again, I was increasing, so di dt is positive. That means I can write V equals L di dt. In this equation itself, if you draw the voltage and current polarities like this, the Lenz's law is already incorporated. So whenever you are writing V equals L di dt, do not just blindly write it. Before you write, check the polarities of voltage and current, then only you can write this. Same is the case for resistance and capacitor also. V equals IR I can write only when the directions are like that. Easy way to remember, in all these equations, if you see, current is flowing from positive to negative side. Means plus terminal to minus terminal.
How it is minimizing the current, sir?
It is not minimizing, it is trying to resist. The current was increasing. Lenz's law said inductor will do something so as to resist the increase in current. How will it resist? By giving an opposite voltage.
Just become stabilized. That's it.
Not stabilize. If you have a source that keep increasing the current like that, it will keep increasing. It may not stabilize. Say for example, if you have a circuit like this, a DC voltage source connected to a pure inductor. If you look at the circuit current after closing the switch, this current will never stop increasing. This will increase forever. If your DC supply has the capability of providing infinite amount of current, and if the switch and inductor can withstand that much current, this current will keep increasing forever linearly. So it may not reach a steady state.
Sir, whatever the sign of the terminals of inductor is, it is the sign of the battery or the voltage source we are supplying to it.
No, not necessarily. In a circuit, you can give the signs the way you want. Only thing is when you are writing KCL and KVL, you have to be careful. You should not make a mistake there.
Okay, sir. And in the inductor, the EMF induced, what will be its polarity?
Again, if it is a DC, if you're talking about DC, say what I have drawn here, this is a DC voltage V, then you will get a polarity like this, positive polarity. This will be V also, no? KVL. Okay, any doubt? Any more questions?
As you said that the voltage rating in Japan is 220, is
110,
110.
110.
Why is it so, sir?
Conventionally, I think they had a thought that lower voltage is less dangerous. The full domestic AC supply there is 110 volt, 60 hertz. In the US also, we will say the same. See the same thing. While in India, the influence is British, so we have like UK 230 volt, 50 hertz in India.
Sir, it is also to minimize the loss in transmission.
See, everything comes for a cost. Reducing the voltage will require more current for the same power. So
Like
losses might not be minimized.
which will be, sir, killer for us, either voltage or like charge or current.
The killer is the resistance that is present in your body.
Sir, then when we touch a DC source of like 10 volt, 12 volt, and many more, then we don't get any shock. But
Then also
there
you
was
get a shock, you do not feel it. See, this is you, okay? Grounded. You touch something here, a current flows. Until the current reaches say 15 to 20 milliampere, you will not, no, to feel it, I think around 10 milliampere, maybe you will start feeling. 20 milliampere is already fatal. 20 milliampere of current is enough to give you a good shock. 40 milliampere will cause death.
okay, sir.
So it
Then
depends on how much current is flowing through your body.
okay, sir. Then what is the amount of voltage that can produce 10 milliampere current?
Human body resistance, I do not exactly know, but it's in the range of mega ohm. I think 10, 20 mega ohm. Then you can find out from there.
Okay.
But I do not know the exact figure. Don't take my word like that. But in the range of mega ohms.
Like that, it's like everywhere I see which is killer, either current or voltage. That's why I asked.
See, the thing is, there is no current source around you. Okay,
Yes, sir.
we will discuss one day about this thing. But there is no current source around you. Maybe in laboratories you will get to see some current sources, but everything that you see around you are voltage sources. Right? So you have a voltage source like this. So this is you standing. This is your hand. Okay. And you are standing directly on the ground. Say this is 230 volt. Directly on the ground you are standing. This will give you a good shock. But suppose this is a wooden plank. On which you are standing. This is still 230 volt, but you will not get a shock probably. If this is thick enough,
Why,
you have
sir?
try this. This is because for you to get the shock, the current must flow through the body. If the current doesn't flow, you will not get the shock. Now what happens is your body has a resistance. So when you are standing on the wooden plank, your body has a resistance, but the thick wooden plank has much higher resistance. So maybe out of the 230 volt, around 210 volt is dropped across the wooden plank. Only 10 volt is coming maybe across your body. So that causes a very minimum current flowing throughout the whole system.
Okay, sir. I think, sir, after 100 volts, if we touch, that may be fatal
No,
for us.
before that also. Before that also, I have seen my friend getting a shock at 40 volt DC. It was painful. Luckily, I did not get the shock because he did. We came to know that it is exposed.
Yes, actually,
But
sir,
unfortunately, he got the shock.
actually there was a discussion in the video, second lecture, I think. Like if ideal current source uh, will be exist, and if a person
Ideal
touch
current source or voltage source?
a current source,
Ideal current source, okay.
like if the person will touch it, it may be it is obvious that that will kill that person.
Yes, ideal current source, no one can save you. Means you can even stand on a 10-kilometer thick wooden block, it will kill you.
Why, sir, that's so
That
much
is
difference?
because as I said, that current source, irrespective of the load, would always supply the same current. Say this is a say one ampere is very large. Say 20 milliampere current source.
Yes, sir.
So it does not matter whether you short circuit this current source or someone comes and touch it. That too standing on a wooden plank. The current will always be 20 milliampere. What will happen is, since now there is enormous resistance in this path, the voltage across the current source will be very, very high. That is a different thing, but this person will get a shock and most probably die because 20 milliampere current is flowing through the body. No one can save.
Sir, but what about like the wood has also resistance now?
It has resistance, but this current is always 20 milliampere. Does not matter what it is. Even if there is no wood, even if say this person is directly standing on the ground, then also this current is 20 milliampere through his body.
Yes,
And
sir.
if there is this wooden plank, then also there is 20 milliampere through his body. On the other hand, voltage source, it depends. So there is an instrument called Megger. It can generate, if you rotate the handle up to 500 volt or more, that is used for insulation test. So when we were doing our electrical workshop in first year, the two terminals, the instructor there, he said that you touch these two terminals with your hands and I will rotate this handle. So all of us, just for fun, got the shock. But he said that this can create 500 volt. How did you not get a fatal shock? That is because this thing inherently has a very high resistance present in series with the probes. So whenever you touch, actually you do not get 500 volt. But if you remove the hand and measure the voltage here, you will get to see 500 volt. You will get to see 500 volt because it is open circuit. There is no voltage drop across the resistance. But as soon as you put the hands, current starts flowing. This is no longer 500 volt.
Can you repeat it, sir?
Suppose, say I have a 10 volt source. 10 volt source. Okay, let us say DC source. I have say 1 ohm resistance here. Okay. Now if I put a voltmeter here and measure, how much voltage shall I get?
So first we have to find the current across.
Okay, so
one.
what is the current? I have put a voltage source, sorry, voltmeter here. What is the current? Ideal voltmeter.
10 ampere.
10 ampere. What is the impedance of an ideal voltmeter?
It's
Sorry. I am getting too much noise from Deepak's mic. Deepak, are you trying to say something? You can type, Deepak, if you want to say something. Yes, what is the current flowing through this circuit?
The resistance of ideal voltmeter is infinite.
Infinite. That means this is an open circuit. How much current flows in an open circuit?
0.
0. So there is no current. So if you keep like this, so this is like an open battery. You have kept a battery just like this.
Yes, sir.
So the voltage that you get here is nothing but the EMF of the battery that we discussed. The voltage of the ideal source inside. Right. Now, when you connect, say, a 4 ohm, then the current starts flowing, 2 ampere current flows, and the voltage that you get here is 8 volt. So unless this load was there, you were getting 10 volt. But as soon as the load came there, the voltage dropped to 8 volt. Similarly, for the Megger also, if you do not touch, only put the voltmeter and rotate the handle, you will get 500 volt, maybe say. But as soon as you touch the terminal, the current starts flowing and there is a drop across this resistance. And what you get is the source voltage minus this drop. So at a very small voltage at the terminal. Manasi, please keep your camera off here. So current flows through your body. Your body has resistance. It causes I square R power loss inside the body, and that causes the shock or death. So
Sir.
the answer to the question is probably power. Power kills you. Yeah.
Sir, the resistance of that equipment is much high, no?
Is very high.
Sir, if we touch, like you earlier said that your friend gets shock on a 40 volt DC. Like if we touch only positive terminal of the battery, then will we get shock, or either
Again, it
we
depends.
have
Okay,
to
we will see.
touch both the terminals?
We will see. You guys have some idea about transformers, right?
Yes, sir.
12 standard physics.
Yes, sir.
Okay. So suppose there is an AC source, right? This side of the AC source is grounded. Okay. And this AC source comes to a transformer. This terminal is also grounded. So current flows, right? Now this is another side of the transformer. And say there is some load connected to this transformer. Okay. Now one person is standing here, which is grounded. So these 3 grounds are the same potential. Now, if this person touches the AC source here, touches this wire, what will happen? A current will flow. Current will flow through the body, through this ground and this. So this person will get a shock. Right? Why? Because current is flowing. Now
Yes,
another
sir.
person, he was also sitting on this or standing on the same ground, but he touches this side of the transformer. This side of the transformer he touches. He will not get any shock because there is no path for the current to flow. Only if he touches this side with one hand and this side with another hand, then he will get a shock. Similarly, you will get to see on the transmission line the birds sit with their legs, one here, another one here. They don't get a shock. That is because this is a transmission line. That means the resistance is very less. Even if you say a current is flowing in this direction, which is the potential difference between this point and this point is very, very less, very, very less to give a shock to the bird. But if this is a big bird which has tail, and if this tail touches another line, the bird will get a shock. Similarly, if some person, do not do this again, holds holds one line with both hands and hangs from a transmission line, he will not get shock. But if he holds two lines with two hands, he will get a shock.
Hello, sir. Can you explain
Yeah.
the what is happening in the second part of the transformer? Like how the man will get shock?
If he touches both the terminals of the secondary, then there is a flow of current, right, through his hands.
Yes, sir.
He will get a shock.
Okay, sir. So we can get a shock either we touch one terminal of battery or both.
So if you talk about a battery, say if you have a large
40 watt.
battery
Yes, sir.
at your home, again I am talking about battery, not the AC source at your house.
Yes, sir.
If you have a large battery like this that is kept on a table, better wooden table, and two terminals, if you touch one terminal, you should not get a shock. But if you really want to test this with a tester. Okay,
Okay, sir.
do not test it by yourself, test it with tester. But do not touch both of them, you will definitely get a shock. And these batteries can supply some dangerous amount of current, lead acid batteries and all.
Sir. And if the wooden wooden table was not there, sir, like
Why I
if
said
it-
wooden table is that is for your safety. Ideally there should not be, but sometimes means what we assume at infinite impedance, that never happens. There is always some leakage current, and if the leakage current is in the range of 10-20 milliampere, you will get a shock.
Yes. Okay, sir.
So it's better. That's why I told you, if you really want to test with a tester.
Okay, sir.
And for this battery I am saying, not transmission line.
Okay, sir.
Yeah, any more questions? Okay.
Sir, how energy is expanded when positive and negative charge are separated?
Do you play with magnets, or did you used to play with magnets as a kid?
Yes, sir. Yes, sir.
So you put magnet on the fridge wall like this,
Yes, sir.
and then you pull it out, right? So when
Yes,
you are
sir.
taking it out, you have to apply some force,
Yes, sir.
and you are also causing displacement.
Yes, sir.
That means you are doing some work. Work means energy.
Okay, sir. Got it, sir.
Again, if you keep this magnet, take this magnet very close to the fridge wall and release it, it will very fast go towards the wall and make a sound. Where did the energy come from? You only stored that energy when you took it away from the fridge. It came from you.
From where this energy come when we little bit keep a difference between the fridge wall and magnet, little distance.
Go. Tell us once again. Say once again.
So like when we go closer to the fridge wall, and we have a magnet, like it acts like the uh, force force between the magnet, and like the refrigerator wall is pulling the magnet towards it.
Hmm.
So how, from where this force come?
It is a stored of energy in the field, no?
Oh, yes.
When you took it away, energy got stored in the field.
Oh.
Sir, electrostatic force is powerful than gravitational force, other than just going through formula that R is small in the celestial bodies. See, I'm an electrical engineer. I don't know about celestial bodies and all. Is more powerful. Sorry, I don't know about these things. I'm electrical engineer, not a physicist. Okay.
Mostly, so most of the times mainly confuses between the words like potential difference, voltage, EMF. That's always confusing.
See, potential difference and voltage are the same thing, and they are the more general term for more general term. Okay, you can take any 2 points in a circuit and say the voltage or potential difference between these 2 points is this. But EMF comes only when we talk about the source of say electrical energy, let us say. That can be a battery, that can be the terminals of a generator. So we will study DC generator at the end of the course, the last lecture, DC machine. We will get to see that there is something inside the DC machine that is called an armature. We show it like this, armature. So what we get here is we call EMF. Sometimes we'll call this EB, back EMF. Or for generator, it is simply EMF. For motor, back EMF. For generator, it is simply EMF. Because it is acting like a source. Electromotive force. It is causing the electrons to flow. Simple. Okay, anything else? All right, we'll slowly go into the questions. We'll see how much we can do today. Have you done this already? Okay, look at the first question. We have already discussed this. Across any two terminals, in case of open circuit and short circuit, the value of resistance will respectively be what? For open circuit, what is the resistance?
Infinity.
Infinite. And for short circuit is 0. Okay, any doubt? This one. All right. Next question. Two incandescent light bulbs of ratings 230 volt 30 watt and 230 volt 50 watt respectively are connected in series across the mains of 230 volt. Okay. So what is the difference between these two bulbs? One is 30 or one is 50 watt. So the difference is in the resistance. And they are connected in series. The bulbs will together consume 80 watt, 50 watt glows brighter, 30 watt glows brighter, same brightness. We'll see. So power is V squared by R. V is same for both. So what we see is from here, P is proportional to 1 by R. So the resistance of the 30 watt bulb is greater than the resistance of the 50 watt bulb, right?
Yes, resistance.
Power is less, resistance is more. So the two resistances are 30 and R50. They are connected in series like this. Now you see, since they are connected in series, the same current is flowing through them. right? And the power through them is I squared R. So if I multiply I squared here and here, so the 30-watt bulb is consuming more power. So it will glow brighter. Right? This will glow brighter. Any doubt?
No, sir.
Okay. Can you find out the total power? Although it is not asked in the question. Just tell me the steps, don't have to do it. If you have to find the total power. Just a second. First step is find the R resistances. You can find from this equation. So once you have the resistance and you connect them in series, you have the total resistance. So from here you can find out the total current I that is flowing. Now the total power is I squared times this plus this. Okay. Okay, we'll go into this. Two batteries with EMF values E1 and E2 and internal resistances R1 and R2 are connected in series with an external resistance R, and the current through it is 3 ampere. When the polarity of the second battery is reversed, the current through the resistance becomes 1 ampere. So initially they had additive polarity, that's why the current was more, right? So initially what we had was, this, like this, E1, E2, R1, R2, capital R. So what we had is E1 plus E2 by R plus R1 plus R2 was 3. Now they are reversing the other battery. Doesn't matter which battery you reverse. It is now like this. So what you have is E1 minus E2 by R plus R1 plus R2 equals 1. They have asked us to find out the ratio of E1 and E2. So we can just use addend to dividend 1. So E1 plus E2 by E1 minus E2 is 3 by 1. So E1 by E2 is 4 by 2 is 2. 2 is to 1. Clear? These are easy questions. Questions I believe will become difficult, more and more difficult in the next classes. Can someone please respond at least once if it is clear?
Yes, sir, clear.
Okay. Okay, you can mute yourself. Okay, we'll go to the next question. Some network is shown, no resistance value is given, and they have asked us to find out this current. Why? Can you Guess or tell what should be this current going into this network. You did not even do anything. Simply forget the resistances. Assume the network like this. So a network which has 4 ports like this. So 9 ampere is going here, 12 ampere going out. Sorry, going out, 4 ampere coming in. So total is 13 coming in, 1 ampere going out. So 1 more ampere should go out. So what is the answer? Y should be equal to I can't hear you, Deepak. It's too noisy from your side.
-1.
-1. Minus because of the direction. The question that y is shown up while current is actually flowing in this direction, 1 ampere. So y is -1. Easy question. Anyway, you guys answer this question. In the circuit shown below, the current through 1 ampere, 1 ohm. What is the current in this branch?
It's 0.
Why?
The whole current will pass through the short circuit path, and
Yeah. So if I want some current through flow through the 1 ohm and 2 ohm resistance, what should I do?
so I think there should be, if we can remove the short circuit path,
That's enough.
or either we can connect a resistance in the short circuit path.
Yeah. Yes, that also will do.
And sir, in this question, the
Hmm.
current through 2 ohm will also 0.
Yes.
Okay, sir.
Okay. Okay, we'll look into this question. When two identical resistors are connected in series across a battery, the power dissipated by the combination is 10 watt. When the resistors are connected in parallel across the same battery, the total power dissipated will be how much? So you have a battery. Okay, before we do this solve this question, you tell me one thing. What is the difference between these three symbols?
The first one is, I think, sir, for voltage source having more magnitude, and the second one is like less magnitude, and the third is like voltage sources are connected in series.
So
Hmm,
that I
Soumya,
think the difference
yeah.
of ideality.
Anyone else wants to try? The first one is a simple voltage source. Okay. The second one is a cell. Say the battery that you buy. Cell. And several cells, when put in series parallel combination, they make a battery. So this is the most general symbol. You can replace a cell also with this voltage source symbol. The symbols have nothing to do with the magnitude. Okay.
Okay, sir. So how will we voltage source will be sir, equivalent to battery representation?
Equivalent to, yes, you can always show a battery like with a voltage source. It doesn't matter. If you want to specifically mention that this is a battery, you can show a battery. But you can show it like this also. It doesn't matter. 10 volt DC.
Okay.
All right, two identical resistors are connected in. Okay, we read the question. So the thing is, there are two resistances in series. The power consumption is 10 watts. So V squared by 2R is 10 watt. And when they are in parallel, then what is the resistance? It is R by 2. So V squared by R by 2. That is 2V squared by R. This is how much? This will be 40. Right? Is it clear or any doubt is there? Just multiply this equation with 4.
Yes.
Okay. Today we got a lot of question about charge. So this is a charge. Probably this is the last. I mean, we almost do not talk about charge in electrical engineering. Almost do not talk about charge. We always talk about current. Very few cases we talk about charge. Anyway. So the current through an element is shown in the figure below. The total charge passed through the element from 0 to 8 seconds is how much? So how to do that? What is the basic formula? Relation between current and charge?
I is equal to dq by dt.
So I is dq dt. So if I have to find the charge, what I have to do from a current waveform, I have to integrate the waveform. So basically I have to find out the area under the curve, right? So find out the area under curve, find out the triangle. So 20 into 1, so this triangle is 10. This is how much? 10 into 1, so 10. 10 into 1, 10. 10 into 1 is 5. Again 10. 2, 10, 20. Make a difference. 10. 10 half 5. 2, 10, 20. 21, 20. Sorry. Again 21, 10. Right? Anything wrong? Did I make a mistake anywhere? Add this up. 10, 20, 30, 40, 45, 65, 70, 80, 100, 110. Right?
Right.
Okay. Do you know what this symbol means?
Dependent sources.
Yes. So this is a dependent voltage source. This can be a current dependent or a voltage dependent voltage source. And the second one is a dependent current source. Can be a current or voltage dependent current source.
Yes.
So this question says there is a current dependent voltage source here whose voltage is given by 2I. So whatever current is flowing here into 2, that much will be the voltage. Can you tell me one thing? This number 2, does it have any dimension? Or is it just a dimensionless constant?
Dimensionless, as it is a constant.
Anyone else? The left side is voltage, so right side has to be voltage. But I1 is current, so 2 must have a dimension of resistance. Okay. This is not a dimensionless quantity. Anyway, so what we have here is 3 ampere flowing in this branch and 6 volt here.
Sir, is it 2 is the resistance of that dependent source?
No, 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 not like that. Dependent source, not like that. It's not its resistance.
Then which resistance it's talking about?
I'm not talking about any resistance. I'm talking about the dimension of this number. Its dimension is same as resistance, ohm. Okay. So determine the amount of power delivered or absorbed by the current source in the circuit given. So the current we know across the current in the current source. What we have to find out is the voltage across the current source. Then only we'll get to find the power of the current source. So let us say we will analyze this circuit with respect to this point. So let this be the reference point. If this is the reference point or the ground, not the ground, reference point. Sorry. If this is the 0 volt point, we'll measure everything with respect to this. So then what is the potential of this node or this point? What is the potential of this point? Tell me quickly. 6 volt.
2i?
There is a 6 volt source here.
Okay.
So basically, what does a source do? Doesn't matter dependent or independent. Source means under any circumstances, this point will be 6 volt higher than this point. So if this is 0, this is 6 volt, simple. Now 3 ampere current is flowing in this direction. So it will cause a voltage drop of 3 volt. Now the question is, which side is at higher potential? Since the current is flowing from left to right, the left side must be at higher potential. So 3 volt drop. So 3 volt higher potential compared to the right side. So this must be at 9 volt. Now we know that the voltage across the current source is 9 volt because this is at 0 volt. We took this line as 0. Now since this is 9 volt, definitely the power is 27 watt. But the question is whether the current source is delivering power or whether it is absorbing power. Okay, so this is any element whose assumed polarities are this V and assumed direction of current is I. If these are the assumed V and I direction, then the power is VI. Right? Now, if P is positive, then this element is supplying power. If P is negative, then this element is absorbing power. Understood? What happens is generally at the beginning, say if you have a complex network, there are several sources inside. Okay, you do not know before you complete the whole solution, you do not know which source is supplying and which source is absorbing power. You do not know the current direction in the network branches. So what we do at that time is we assume some direction of current everywhere and find out and solve the circuit. If our assumption was correct, we get a positive value. If it was not, we'll get a negative value. It doesn't matter. Now, after the solution is done, if you see, if this thing happens in a source, that the source had polarity like this, plus minus voltage polarity, and you assume the current like this, and when you find out the power V into I, it comes to be negative. That means the source was actually absorbing power. It was not delivering power. So in this case, we have the first situation. We have voltage polarity like this, 9 volt, absolute voltage polarity 9 volt, and 3 ampere. So this was delivering 27 watt. Anyway, so 27 was the only option delivered, so it will be 27 watt delivered. not a very good choice of options. Anyway, so it is 27 watt delivered. Now the
So how
question
you
is,
so
Mhm.
how you get 9 volt, 6 volt? Uh,
Okay, this voltage source will have a 6 volt. This is a 6 volt voltage source. Is that clear?
say it's clear.
Okay. I assumed this point to be 0 volt.
Okay.
That means I will measure all the volt points with respect to this point. Okay. Now this is a voltage source. That means its top terminal is 6 volt higher than its bottom terminal.
Yes, sir.
So if this is 0, this is 0 plus 6.
Sir.
So this is 6 volt. Now there is a current flowing through the resistance in this direction. Resistance is 1 ohm. So the voltage is definitely 3 volt across the resistance. But the question is in which direction? Through a resistance, current always flows from the upper higher potential to lower potential. So definitely my left side, say I say point A, was at higher potential than point B. How much
Yes,
high?
sir.
3 volt high. So 6 plus 3, 9.
Got it.
Now 9 into 3, 27. Why positive? We saw. Why? How do you know that it is delivering power? Now,
So like you have drawn the direction of current from a voltage source
no,
in
from the current source.
and you have written P is equal to VI here one.
Acha, here, okay.
Uh, uh, so the
This is not a
so
voltage
then
source. This
direction.
is not a voltage source. I said any
Okay.
circuit element,
Okay.
which across which you assume the voltage direction to be like this, and the current direction to be like this. Yeah, go ahead.
Then sir, normally we assume that current is flowing from high potential to low potential. Then
No, no, no. It's not normally we assume. It's like this. Say what I told. You have a large network, several resistances. Okay, several sources connected, very complex network. You do not know the direction of current anywhere. What do? Say you have a voltage source like this anywhere. What we do is we simply assume that the current is flowing in any direction, whatever. I can assume it like this. Sorry, current. I can assume it like this. Someone else solving this problem can assume it the other way around also. Current in the other direction. Doesn't matter.
then the resultant value of P will decide is the element was supplying power or
Supplying
absorbing power.
or absorbing
Yes,
power.
yes.
So only if you draw like this. Let me sorry. Separate this out. So only if you draw like this, that plus minus and current leaving the positive terminal, then only you can say if P equals Vi is positive, then it was supplying. If it is negative, it was absorbing.
And
Say
sir,
for
if we
example, in
reverse,
resistance, just a minute. Say for example, in resistance, what we drew here, you see you drew the opposite. You said current, we drew here current is leaving the negative terminal. That is why the power P that you get here, IV, although in this case we will get it positive, the power is actually getting absorbed because this drawing is opposite to what we drew here. Clear?
okay,
There
sir.
we drew like this.
And sir, if we assume the direction of the current like the like uh, flowing from positive terminal to negative terminal,
Then this
and
thing
then we
just
calculate
changes. Then this
P
thing
equal to
changes. Then
VI.
we have to say P greater than 0 is absorbing, P less than 0 is
Okay,
supplying. Simple.
okay, sir.
If that confuses you, you can just draw it separately in a copy like this. say this is a voltage source. Source gives power like this. So this Vi is definitely positive, and this power is also, and this element is definitely supplying power. So in this case, if P is positive, power is supplying. It's all about how you assume the direction. What I wrote here, if Vi is positive, it is supplying power. This is true only if you draw the voltage and current like this. Okay, is it clear?
Yes, sir, clear.
Okay. We'll do this problem in some other, not some other way, same way, but I will just show you. It doesn't matter where you take your zero voltage assumption. But some things do not change. What are the things that do not change? That this will always create a 6 volt. Okay. Now what we will do is we'll assume, say this is the 0 volt point. So if this is 0 volt point, what is the voltage here?
-6
Hmm?
volt.
How much?
-6
Minus
volt.
6. And what is the voltage here? What is the voltage here? 0 plus 3 like before. 3 volt. It was 0 here. 3 volt above because there is a drop of 3 volt across the resistance. 3 volt. So the voltage polarity that I have drawn across the current source, based on that, if I ask you what is the voltage across the current source, you will say 3 minus 6, 9 volt. We are getting the same thing, right?
Right, sir.
Now the question is, this current source was delivering 27 volt, sorry, 20, oh, I wrote power 27 volt, 27 watt of power. Where is this 27 watt of power going? It must be going somewhere. Energy conservation. Can you tell me?
Like current source was delivering power 27 watt, then the resistance was dissipating the power
How
up
much
to
power
3
is it dissipating?
this I square are like
How much?
9
How much? How much
9 watt
watts?
9 watt.
9 watts. And where is the rest 20, rest 18 watts?
I think it's from the dependent source.
Yes. So see, in the dependent source, current is flowing like this. 3 ampere. Right now, if we draw this dependent source as per what we drew here, I have to draw it like this. This is 6 volt. Here I drew the current like this. This is minus 3 ampere. So what is the power? Minus 18 watt. Minus means absorbing. So this source is absorbing power. Like say charging a battery. A battery is a source, but when you are charging the battery, it is actually absorbing power. Cool.
Okay, sir. Like
Yeah.
it's 18 watts, sir, and the current is flowing from positive terminal to negative terminal. Since it
Yes.
is positive, it will be uh, absorbing power.
Absorbing power. Yes.
Yes.
Since current is entering the positive terminal, it's absorbing power.
Okay, sir.
All right, look at this question. This looks like a joint entrance question. In the figure shown below, if n equals 15 and R1, R2, R3 all are 1 ohm. So first one is 1 ohm, second one is 2 ohm, like this, 15 ohm. Voltage drop across the 10th resistor. So what is the total resistance, equivalent resistance?
NRN.
No, NRN is the last one. They're in series. What is the total equivalent resistance? Right? 120 ohm. So what is the current? This much.
180. Yes, sir.
And voltage across the how much? Oh, it is R, sorry. R. And voltage across R10. What is the value of R10? R10 is 10. So 48 by 12. 120 into 10. 48 by 12. 4 volt. Right?
Yes, sir.
Okay. Let us see. A stove element draws a constant current of 10 ampere when connected to a 120 volt DC supply. How long does it take to consume 18 kilojoule? So what is power? Power is 1200 watt, and energy consumed per unit time is power. I should write capital T. So T is energy by power. So 18, let me write like this, kilojoule, 15 second. Right?
Okay, sir.
Any doubt? No doubt. This is a 10th standard question. You guys want to solve this? That load of a household consists of 6 lamps of 20 watt each, 4 fans 75 watt each, television set of 50 watt. 50 watt television set? I don't know. Refrigerator of 180 watt, air conditioner of this much, electric heater this much, washing machine this much. Supply is 230 volt. For an average loading 50 to July. Okay. Can you solve this or you want me to solve this? Quickly, tell me. Have you read the question? Okay, let us solve this.
Yes, sir.
So 6 lamps of 20 watt. Do the calculations for me. Okay. 4 fans of 75. Television set, refrigerator, air conditioner. What they do not have: electric heater, washing machine. Can you tell me? the summation quickly. 150, 300, 120, 420, 500, 600, 650, 2150, 3150.
500,
Once again, tell me the digits.
5,000, 5150.
5001.
5150. 5150 watt. And they say that average loading of 52% throughout a day, obviously, because they have washing machine and air conditioner, they do not turn them on throughout the day. At least the washing machine should not run throughout the day. So average power is 52% of this. Can you find out 52% of this? Quickly.
2678.
2678
2678. Yes, sir.
watt. So what is the average energy consumed per day? So 2678 watt times 24 hour. So this much watt hour. Can you tell me the value in kilowatt hour?
$64,272.
Kilowatt hour?
64272.
64.27.
64.272. Let us check once. 52% throughout the day. Yeah, it's correct. So this
So
much is
what
the
it
unit.
so
Go
what
ahead.
it means, then for an average loading of what it means?
Average loading means, see, all these loads are not turned on throughout the day. Okay. Basically, they made your life easier. Otherwise, they could have given you a table that this lamp is turned on from 7 a.m. to 8:30 a.m. Air condition is turned on 7:30 to 8:30. In that way, you could have find out the total energy. They made your life easy. They said average loading is 52%. Means what you have total, 52% is the average power. So the average, basically, when you say average power is not a very well defined term. Better to say average energy is this much. That is, this much energy is consumed per day. 64 units, right? Kilowatt hour is the unit. This is the average power. If you look, maybe at night power is something, morning time AC is off, but maybe the heater is on. So month of July, what is the total? This into 31, right? Can you tell me this into 31 how much?
$1992 decimal 432. 1992.
Okay, we'll let it go at this 1992 kilowatt hour. You know this, right? Kilowatt hour is what we pay for. When we say 1 unit, it is kilowatt hour. So cost breakup is like this. For first 800 units, so we'll break this up. 800 plus for next 600 units, 600. We still have 592. So what is the total amount that they are going to pay? Meter charge is 150 plus 456. So 800 into 4, 600 into 5, 592. How much is it?
$9902.
9902. Quite large amount of electric bill, isn't it? For a household. We don't know how many people live here. 6 lamp, 4 fans, 1 television set, refrigerator, air conditioner, maybe a family of 3. But still, it's quite high. Maybe they use a lot the AC. Anyway. Last question for today. Basic philosophies behind KCL and KVL are what? Tell me.
Conservation of mass and conservation of energy.
No.
Sorry, conservation of charge and conservation of energy.
Yeah. So basically KVL says that summation of IV is 0. Right. So whatever energy, so IV is power. So summation of power is 0. So whatever power is being supplied in the circuit, that much power is consumed in the circuit itself. So it's conservation of energy. And KCL is a direct conservation of charge. All right, so we have done the problems for today. 2 more minutes left for today. If you guys have anything to ask, I will answer or we'll wrap up.
Sir, will you post that today's session on YouTube?
Yes, I will.
Sir, can you share the link?
I think you will get to see those in the course page only. The NPTEL people will share some link. If they do not, let me know. Okay, wait for a second. Okay, I will tell you where to find. Before that, let us complete this session. If you have any doubt, I will stop recording, then I will tell you where I will get to find.
Okay, sir.
Sir, I
Yeah.
see previous doubt discussion because I have not received appropriate notification from NPTEL. 29 July come notification.
You will get to see them in the YouTube channels of the respective instructors of those sessions. All of us are uploading. I think NPTEL will share with you the links.
And sir, week 0 assignment and week 1 assignment we submit at that time.
There is some deadline which you have to meet.
Week 0 means exhausted, but week 1 remained.
I'm sorry, what?
Week 0 date expired and week 1 remained some time to submit.
So you can submit week 1, quickly submit it.
Yes, sir.
Okay, I'll stop recording then.